There we go. So real open-ended question. I like these because there are a lot of possibilities. They can be difficult, but usually the answer is up there. This one is a little trickier because, like I said, you don't have any y-axis to help you read it from. But let's see what you thought. Denise, start us out. What did you write down for, what do you think about what this graph is showing us? Yeah, color wavelengths. I did not spell that right. Hold on. I'm sorry, repeat that again. It's showing the color wavelengths. Oh yeah, so from the colors that we separated from the spinach. And what were those colors? Yeah, so it's kind of showing something about the color wavelengths of the plant pigments, and very specifically, wherever that we see there's bumps, that has to do with the color wavelengths. So what should be, it's not here, but if we did label the Y, we would use this word, A, B. Can anybody? This is the physical characteristic or trait of these different pigments that we're measuring that's making those bumps. What was that, Lucas? Absorption or absorbance, same thing. So how well those pigments are absorbing the different colors, that's what it's showing. The color wavelengths, absorption levels. So if the bump goes up, it means that color is being absorbed. If the line is low, that color is not being absorbed. So up here, it's being absorbed well. If it's down here, it's not being absorbed very well. So not absorbed. I'll just put that. So if you look at that, what colors do these pigments like? Kimberly? Yeah, what colors does the spinach like? What do they like to absorb? Huh? Do they like green though? Do you see a high level absorbance of the color green? Yeah, well, you see a bump where it's red and orange, right? Yeah, where else do you see a bump? So wherever you see those high bumps, it means it's absorbing that color. It's liking that color. It's taking it in. I would say the blue, right? The blue is the strongest one, right? So if you say, what is the favorite color of plants, you probably got to go with what? Blue. Okay, and kind of that, almost that purpley range, right? So plants like blue, we'll say blue purple or blue violet, like best. And a close second, well, maybe a distant second, is orange red. We'll say red orange based on this evidence. Okay. What color are they not interested in absorbing? Yellow and especially green. They just don't like green. Okay, and that can kind of confuse us, right? Because plants are green. But remember, you're seeing a color because it's being reflected back at you. So it's rejecting, plants are rejecting the color green. and they're accepting blue and red. So you don't see those when you look at a plant. You see that rejection color, which is green. So plants, photosynthesis, they're not using that green wavelength. They're using the blue and red wavelengths. And if we look at the way, like blue purple, what wavelength does it look like they're liking? It looks like, if we just look at the biggest ones, it's around here. So what would be this wavelength here? Roughly what? Here's 400, here's 500. Each tick mark, what's the value? How many numbers does each tick mark contain? 20. Yeah. So what's your judgment? About 420. So it really likes about 420, wavelength of 420 nanometers. That's terrible. 420 nanometers. So it likes that. And if we kind of look at the red range, we're kind of looking at this. So what would that be? 660, about 660. Based on this data, I got to double check what the accepted values are, but I believe they're very close to that. And I was really amazed. Like I told you, this is the first time I've ever done this. I didn't even know about doing this until Wednesday. But you guys did a great job running the computers and recording all those lines and analyzing it. And it came out to basically what it should be. Now for number 2, each pigment is slightly different, isn't it? Like if you look at, for example, chlorophyll A and B, chlorophyll A maximum absorbance is right about there. Chlorophyll B is a little bit before it, right? It's a little bit shorter wavelength. A little bit shorter, yeah. And over here, same thing for on the other end. Chlorophyll A is a little bit longer in the red than chlorophyll B. So they're slightly different. Now, why is that? Why do these different pigments have a different absorption rate? Jacqueline, what's your guess? What's your thought? You don't remember? No thoughts? Okay. Annabelle, well, what could be causing that? Each one, and they all traveled different lengths along the paper, didn't they? So that could give you a little hint for why this might be different too. What's your thought, Annabelle? Want me to guide you a little bit? So check this out, Annabelle. Do you remember what I said with why some of them went further on that paper, some of them didn't go as far? If you were a pigment and you're traveling along, are all the pigments going to stick to the paper the same way, do you think? No, they're all different chemicals, right? So they all have different levels of stickiness, most of it because of hydrogen bonding, what kind of atoms they have sticking out there to stick, bond with the paper. They also are all they're dissolving in the petroleum ether acetone mix. Do they all dissolve the same way? No, so they're different chemicals, so they react differently on the paper. So what could that mean about how they react to light and how they absorb light? They're different chemicals, right? So they might what? Might need more energy for no, still need help. Okay. Anybody else? They're all different chemically, so they travel different lengths. When you shine light on them, could those different chemical properties also affect how much they absorb light and what wavelengths they absorb light? Yeah. If they have different chemical properties, they're going to absorb light differently. Okay, how the bonds work, how the angles work, that's going to affect their light absorption too. So just like their different chemical properties affect how far they travel on the paper, the same different chemical properties affect how well different wavelengths get absorbed. Okay? So let's say different chemical properties for each pigment affects how well each is absorbed. Probably could have explained it better than that, but hopefully that's sufficient. They're different chemically, so they're going to absorb differently. Just like they're different chemically, so they travel different lengths on the paper. But I thought it was really impressive. You guys were able to chemically separate them and analyze their different characteristics. All right? That's next level. That's good stuff. Okay. Tomorrow we'll get back into genetics. Are you guys almost up to, what did I say, 175 in your biozone? So try to get there best you can, because tomorrow we'll get into it. Doing a bunch of more Punnett squares and doing some more calculations with that. Okay? But now we're going to do a little fun activity because it's springtime. Last Thursday was a special day. Okay, I want you to think about why. And it's part of the questions you're going to answer today. Okay?